Let's get started. So the speaker today is Dr. Gary Hunter. Let me make a brief introduction before he had taken over for the seminar. Dr. Hunter right now is a technology leader for the sensor research at NASA Glenn Research Center. Specifically, he's in the division of Smart Sensors Electronic Systems branch. And he has a long career for sensor research development. When I look over his bio, he's a very prolific inventor for commercial application of the sensors. Since he arrived at NASA Glenn, he has been dedicated for the design, fabrication, testing of a variety of type of sensors. For example, there are high temperature wireless sensors we just talked about last night and also minutes ago. That was a feature article in Science magazine back in November. And also his research involved engine emission sensors for environmental monitoring, fire detection, and leak detection. And some of his research really end up in a real scenario, applications in a variety of NASA mission and in the, as an example for the NASA launch vehicles. And also he developed some of the fundamentally new techniques for fabricating sensors. As a result of his long-time accomplishment, he got a few awards. So among them, in 2007, the activities he co-managed was recognized by one of the NASA's top discovery stories of that year. And in 1995, quite a long time ago, and he received one of the R&D 100 award. So this is recognition of his very significant innovation associated with automated hydrogen leak detection systems used on Ford automotive assembly line. And 10 years later, he received another R&D 100 award, which I think is very significant, and for the fire detection, which showed zero false alarm rating in the FAA testing, which is remarkable. In terms of education, so Dr. Hunter has taught a few courses in the area of chemical sensing, high temperature sensors, electronics. He co-authored a few book chapters, and he is also co-supervising one of our PhD students at the Tailor, Tim Paulinski. He's in the audience. So my hope is by having Gary here today, he can hopefully bring NASA research more close to what we are working on this year. Now let's welcome Gary.
John, thank you very much. Appreciate it. I thank you. All righty. Hello, thank you for having me here today. I'm Gary Hunter. I'm from NASA Glenn Research Center, and I'm in the Smart Sensors and Electronic Systems branch. And we are going to talk about the importance of intelligent systems that sometimes don't work. Tell you what, we're going to get out of that mode, and I'm just going to go to this mode. Let's see if that works. Okay, then because that part worked earlier. Yay! All right. I have often talked about the importance of intelligent systems and then watched the computer crash. But one of the things I think I might suggest in this presentation today is that we are moving towards more intelligent systems. They provide more capabilities. And if we're going to achieve things that we haven't achieved before, we're going to have to, in my opinion at any rate, become smarter in multiple ways, including the intelligence embedded into our systems and how we operate. And so now let's see if this part works then. So I'll talk about sensor platforms and smart sensor systems, harsh environment smart sensors, discuss a bit microsensors based on nanostructured materials, and give a summary and a conclusion. And so I come from the Smart Sensors Electronic Systems branch. We do a range of things in that branch. They include high-temperature electronics, MEMS, nanotechnology, chemical sensors, and thin-film physical sensors. And we have capabilities and facilities at the center to be able to do a range of, in a sense, making our own sensors and designing our own sensors associated with applications that are beyond those of commercial technology, beyond those that are standardly done. And I hope to show some of those as we discuss things today. But this is sort of a feeling for what features we have. Two separate clean rooms, one for dirtier processes made in a sense, in making chemical sensors, and the other for making electronics, and electronics that are meant to operate in harsh conditions. And the core of what we're up to in terms of smart sensor systems is shown here. The idea is that embed intelligence inside of the computer system as much as possible. Some sensors may just be a sensor itself, but if at all possible, move towards microsystems, that a sensor isn't just an element, isn't something that measures something, but it is a complete system made of packaging, communication, power, electronics, providing information to the user. In this information age, it's suggested that small smart sensor system technologies are an enabling first step in acquiring information about aerospace systems or the environment, leading to understanding the environment and leading to decision making. You can't make a decision in a sense if you don't know what's going on. Trying to find out what's going on, in other words, sensor technologies is a first step in that regard. And so, sensor system implementation has often been challenging. What we're moving towards is self-aware intelligent systems composed of smart components. But sensor systems are necessary, but not just going to show up when you need them. The idea is that there should be interaction between the user and the developer, that the sensor should be tailored for the application. Often folks have tried to take a sensor that right off the shelf, not meant for that application, stick it into the different application and find it didn't work, thus blaming the sensor. We would suggest that you need to tailor the sensor for the application, and that should be a partnership in the sense between the users and the developers. Sensor system implementation is often problematic. You have legacy systems. We've done it this way before. Why should we change? In some fields, change is very rapid. In other fields, it may be less rapid. For example, in safety critical applications, say aeronautics, potentially space applications and the like, the idea that we have done this for a period of time, we're not sure we trust your technology. In the long term, it may be better, but I've got a budget to meet, I've got a schedule to keep. And so, sensors often need to buy their way into an application. Even if, in the long term, they may have significant impact, they have some steps to get over in order to be accepted. Some general directions in sensor technology include increased miniaturization, making things smaller, adding intelligence, increased intelligence, multifunctionality, multi-parameter measurements, orthogonality, and I'll get to some of this on the next page. Increasing adaptability. Why would you like a microprocessor? Why would you like to embed intelligence into the sensor? In part to be able to allow it to be adaptable and to understand its status at any given time so as to give better information. And one of the directions in sensor technology is what we're calling lick and stick technology. I described that further, but the idea that you move with complete systems, that you have a complete system associated with your sensor, not just an element, not just a chip. And so the basic approach suggested for making intelligent systems from smart components is the idea of first lick and stick technology, as we're phrasing it. Make it small, make it smart, embed intelligence into it. If every time you're going to try to put a sensor on, you're trying to put a bread box on, you have a problem. So make them miniaturized so they don't impact the vehicle or the system that you're trying to measure. Reliability. People would often not want a sensor if they give confusion. They'd rather have no information than confusing information. They try to often kick sensor systems off the vehicle because they don't trust them. Well, in order to make them trustworthy in part, back to the lick and stick approach, embed intelligence so the sensor can, in fact, know itself, redundancy and cross-correlation. If they're small and if they're smart, then put a number of them in a region. Let them back each other up and let their total information that's brought in help reinforce each other and give a better feeling for the environment and, in the end, orthogonality. When we try to understand this world, we do it with 5 sensors. We don't do it with 1. But sometimes folks would want to take a measurement and only measure the thing they want to measure. Temperature, for example. One suggestion is have multiple sensor systems, and this seems, yeah, there we go, so that your information is orthogonal, that they're not overlapping each other, that it's different pieces, different sets of information, so as to understand the environment. So, smart sensor system development, the idea is that each sensor platform, that we start to move towards sensor platforms and sensor systems, and each sensor, and for us it's chemical sensors, has to at least have some basic properties. They got to have a response time, sensitivity, selectivity, and stability that are appropriate for the application. Also, we've been moving towards batch fabrication, the idea that you, for example, make 100 sensors at the same time. It's part of making them small in batch fabrication processes and clean room processes. Tailor the sensor system for the application. Mentioned that a moment ago. And often the application can be very specific in terms of what you have to do to the sensor to make it work. That's the basic sensor, but packaging and other supporting technologies are mandatory. Packaging can be a major component of making a sensor system. Signal conditioning and processing to make sense of the data is necessary. Software, call it neural net or whatever it might be, some type of supporting information, whether on the sensor itself or off board, is necessary, and power and communication. And so our basic approach is to combine miniaturized sensor platform technology with adaptable smart hardware platforms to meet a range of application needs. And this is with respect to the chemical sensor program. Down here we have 4 different platforms. Electrochemical cell, actually 3, but this is an electrochemical cell. This is a resistor. This is a Schottky diode, and so is this with a resistor. These are basic but these are made of different materials and thus have a different application range. From these basic platforms, from these basic structures, the materials are changed, the structures are changed for the individual application, and from these basic structures of Schottky diodes, resistors, and electrochemical cells, we've addressed applications ranging from fire detection to environmental monitoring to leak detection to emissions monitoring and the like. Start off with that core, adapt it as necessary. Here's an example of one of our first technologies. This is a hydrogen leak detection sensor, and the idea is that you have temperature detector and heater to stabilize the temperature of the sensor. 2 types of hydrogen sensors, one for low concentration, the Schottky diode, one for high concentration, the resistor. The whole thing is approximately 2 millimeters, and there it is on top of a standard standard package. Moving from that platform, this is a silicon carbide gas sensor. It is also a Schottky diode, but instead of a silicon semiconductor, this is a silicon carbide. This can go up to 500 degrees C and beyond in temperature, and it is meant to address another range of applications, but it is, in a sense, based off of one of the same platforms. The next sensor has to do with the resistor, and the idea of people have been using tin oxide for a good period of time as a resistor, as a sensor. This here talks about doping of that tin oxide, so it has a whole different set of properties than what is previously done before. So to go back to what was said a couple slides back, the idea is to take sensor platforms, adapt them to the application through change of materials, and even the core, say semiconductor in this case themselves. This is some of the examples associated with the application of the hydrogen sensor technology. We'd like to note that these are a number of different applications, and in the bottom here, I seem to have, there it is. In each case, the associated hardware that goes with the core sensor needs to be modified for the application, going all the way from an umbilical cord setup to something that is mounted on the side of a, I seem to be losing this every 30 seconds or so. At any rate, a mounted on the side of the, in this case, the shuttle. Each case, modify the hardware, modify the supporting technology in order to meet the needs of the application. Yeah, at least that part's still working. Okay. And so one of our applications over time was gas sensors for low false alarm rates. One of the issues, and this was around the turn of the century, and I know that seems like a while ago, but the bottom line was that folks were having problems with the false alarms rate in the cargo bay of aircraft. And what was happening is that they were using particulate sensors to detect whether or not there was a fire in the cargo bay. Other things can trick the particle detectors. Unfortunately, literally, there were, as I understood it, animals on board. What they let out over a period of time tricked the fire detection system that set off an alarm that then purged the chamber, unfortunately, for the animals involved. It was using a single type of technology trying to understand an environment that was much more complex than that. So the idea is to take and begin to go at this with multi-parameter detection. Not try to understand the world only in terms of fire, in terms of particulate detection, but also have a range of other species monitored at the same time, things that are related to a fire, such as carbon monoxide, carbon dioxide, other species, as well as particulate. So what one sees here is something that is reflective of the particulate measurement, but also a range of other species that are associated with potential fire detection. I'm going to see if I can get a backup pointer here. And by the use of those multiple parameters, then be able to take and understand whether or not there was a fire. In testing in the cargo bay at the FAA, what had happened is that was that we set a fire literally in the cargo bay itself and tested the standard fire detection system and this multi-parameter approach. And what happened in the end was that there were no false alarms associated with the multi-parameter system. There were false alarms to humidity and dust associated with the particulate detection system. And so that basic principle of looking at the system with multiple approaches, we have tried elsewhere. We've tried to, for example, move it towards space technology because a fire, for example, on the space station is problematic, and have put in a range of species so that you're not only dealing with now fire detection technology, but environmental monitoring, not only dealing with stationary systems, but also handheld units as necessary. And so we've also looked at taking this into a wireless type platform with a central node and where you might have sensors move, in this particular case, across the station. So as, again, part of some of the original slides early in this presentation noted, cross-correlation from multiple sensor units within a region. And so another one of our areas had to do with breath monitoring. This was back in 2007 or so. This was a breath conference associated with the Cleveland Clinic, who we then worked with in something called the Ohio Third Frontier Program. And that work was associated with the idea that there are a number of species that one may emit in the breath, and they can, in some cases, be correlated to disease conditions. The most advanced of these is asthma monitoring. The idea is that around, and in one's breath, around 10 parts per billion of NO is relatively normal. If you start to get, for example, towards 100, then that's indicative that the medication isn't working, that you may be moving towards an attack. And so the idea of being able to have mobile systems that can, for example, be brought to the home, these are not these are just examples of mobile systems, but the idea that you should have home health care, that the idea that you could breathe into something, it would tell you your health state and transmit the information to the doctor, is something that folks have been talking about in terms of improving quality of life and decreasing the cost of health care. And so, back. Please go back. And there. So our job in this is that this was a technique used by Ohio State University that had the sensitivity to be able to detect nitric oxide at those levels. And our job then was to take this and make it smaller and smaller so that it would be able to fit into a system such as this. The idea is increased miniaturization, but there are challenges associated with that. If, for example, the sensing properties are proportional to something having to do with the surface area of the system, then one had to design it in such a fashion to maintain the sensitivity, but while you're decreasing the size of the system. And so that was a challenge for us over a number of years, some data showing ability to get significantly down associated with the ability to detect NO. And this is what a system might look like. There might be other versions of that going forward. And so the idea is in terms of this lick and stick approach, I may have just skipped a slide. 1 second, please. Let me go back. Yeah, this thing has been working on... There. I think it just skipped a slide earlier. Thank you. I don't think I did this slide, right? Okay, I'm just going to go by hand. So the idea is that this is the lick and stick approach. What you have here is a microprocessor, 3 different sensors, different ways of communicating. The basic approach is to need multiple applications building from a core set of microsensor technology. This is an example of the orthogonality approach. Hydrogen, flat line, hydrocarbons, oxygen. Each sensor measuring something different, each sensor providing a different bit of information on the environment. And that approach has been used in a range of applications then, again with the principle of changing your hardware as well as your sensor to meet the needs of the application. From the jet engine emissions, aircraft fire detection, breath monitoring, measuring fuel cells, cryogenic monitoring, and other applications. And so that is a discussion of the smart sensor system approach based on silicon technology, based on the type of stuff that might be within our, for example, within our cell phone. As you start to go to more harsh environments, things like semiconductor technology are not as mature. Things that operate above, say, 300 degrees C, there's silicon, say 120 or so degrees C, silicon on insulator, based on silicon to 300. But if you start to go beyond that, you have problems associated with the durability and capability of the electronic systems. There are a range of high temperature applications that, for example, would be of interest to NASA, space exploration, say for Venus, radiation environments, high temperature engines, and, for example, distributed engine control and more electric vehicles. And the approach, however, is basically the same. The idea is that to take a range of sensor technology, integrate it with intelligence, and move towards, in the long term, high temperature lick and stick technology. With the understanding that the electronics is not what you see in silicon-based, it's not a Pentium-based system. And so this would be a less mature set of technologies, but the same fundamental approach, embedding intelligence, multi-parameters, make it a smart sensor system, is in play for both. And one set of sensor technologies that we have associated with this is multi-parameter thin film sensor technology that are microfabricated, in some cases embedded onto the surface. This is a multifunctional sensor array, temperature, strain, and heat flux, all in a relatively small area. This is part of the idea of being able to understand your environment. There's also MEMS-based technology, where one might have, again, harsh environment systems operational at high temperatures and able to be miniaturized, as shown in the wafer here and this picture here of the package sensor, so as to start moving towards a smart sensor system. One thing, though, associated with the electronics is that if you start looking at the temperatures associated with a jet engine, as you go up in temperature and as you go towards the combustion chamber, the ability to have electronics and systems operational becomes problematic. And only some materials, like silicon carbide, as a semiconductor, have a capability of operating in those environments. The approach overall, though, is to have smart sensor systems that might be distributed across an engine, feeding information to a node, and then feeding information to, this would be the engine controller. Have it distributed so that you're not dealing with wires going across the system. You're not make them wireless if at all possible. Don't depend on a single source for all the processing, but distribute the intelligence across the system. One of our projects that was moving towards smart sensor technology was something called VIPR, Vehicle Integrated Propulsion Research. It had a number of folks involved, and what it had to do with was the idea that one will try to monitor the engine using, again, multi-parameters, and in particular, watch degradation of the engine associated with the ingestion of volcanic ash. Well, the reason that a number of folks were involved, one might say, was because volcanic ash is an issue associated with air traffic. Europe was shut down for a period of time when a volcano erupted, putting volcanic ash into the atmosphere. The idea that you understand what levels of volcanic ash you can put in and how you can measure the effects on the engine were some of the drivers associated with this program. And this is another point that I can make with respect to development of sensor technology. Our approach was effectively learn by doing, or as time went on with these various VIPR tests, increase the complexity of our measurement system, increase the complexity of what was available to measure the engine, to the point when we completed the program, we had a range of technologies attempting to monitor the jet engine. One of those had to do with high-temperature electronic nose. Often noses in the commercial sense have the same sensor tweaked several different ways. For us, and as you may have seen by this point in the discussion, we go with orthogonal technology, and so that each sensor, hopefully, will be able to tell you something different about in the environment. And we started off earlier on with technologies that were associated with, for example, O2, CO2, and CO at the back end of a jet engine. And this is a JT-12 jet engine. And by the end of the program, we were dealing with, and this was the volcanic ash work, the idea that we had a whole range of technologies, CO, CO2, oxygen, hydrocarbons, and NOx, monitoring the back end of the jet engine. And as volcanic ash was ingested to it, and this is the data at the end of the testing, there were changes associated on this particular day associated with the ingestion of volcanic ash that we couldn't necessarily correlate to other parameters. And so it does suggest of changes in the engine state due to heavy volcanic ash deposition. But in order for this to happen and for this to be understood, one needed a range of technologies from oxygen to NOx to hydrocarbons and CO and a basic understanding of how the engine, that is, that the engine was stable, and thus the changes occurring to it may have been due to other things happening to it, perhaps the ingestion of volcanic ash, for example. And so that particular test was basically sensor systems in harsh environments. Since then, there's been some advancement associated with high-temperature electronics. And at this point, well, we're at the stage where we're at the moderate level of complexity. By that, one means tens to hundreds of JFETs, transistors in a circuit. Now, when you start dealing with things like Pentiums, you're dealing with many more transistors than that. But at this point, but if you also go back, however, to things like Viking and early exploration, the idea that one can do a lot with basic levels of technology has been in play. This is some examples of the work. This is a 24 transistor ring oscillator, a two-stage operational amplifier. And these, for example, were operating, in this case, 4,000 hours. This was near 4,000 hours at 500 degrees C. We've since then gone beyond that and have had systems operating in Venus simulated conditions for 60 days and nearing a year associated with their operation in a 500 degrees C and in a oven. And so what this has led to, and where we're at now, is something called LISI. LISI means Long Live In Situ Solar System Explorer. It is meant to be a Venus surface station, a weather station to stay on the surface of Venus for extended periods of time. At least 60 days, perhaps 120. The longest anything previously has been on the Venus surface and lasted was for roughly 2 hours. And so this is meant to be in situ on the surface with electronics, with multiple sensors, to be able to provide real-time information as a function of time in an extended duration on the Venus surface. Switching modes then, now microsensors based on nanostructured materials. What I've described so far is the basic core and the application range of smart sensor systems, trying to move that over the high temperature technology. And this is going to talk about nanotechnology for a few moments. And so one thing that one can say is that perhaps we've been doing nanotechnology for 100 years. It's called chemistry. And so what is different from nano? What is the idea that, what is the impact of nano? And why, in a sense, should it be something that we would hope to be able to make major changes? Well, one of the ideas is that users do not care if it's nano. What they care about is new capabilities and something that can allow their application to, in fact, be improved. And so some of the same things that are in play associated with microtechnology, some of the smart sensor systems we've talked about, still are in play. The idea that one has to worry about packaging. You can only go far as your supporting technologies. That if you have a sensor system, you need sensitivity, selectivity, and stability, and the like. So the areas that we had focused in terms of nanotechnology had to do with being able to control the nanostructure, control the system, so that you could be able to make sense of what you were getting and make it reproducible. This includes improving nanostructures, improved nanostructure to microelectrode contacts. nanostructure material control, and expand the range of the nanostructures available. And one of the issues we feel associated with this is often people attempt to, in a sense, drop nanotechnology onto a surface and measure across something that is ill-controlled, and one would have to be hopeful in terms of how reproducible it is. In microtechnology, we can control surface structure. We can reproduce things. In some areas of nanotechnology, that's more challenging. And so what we attempted to do was introduce some of the same types of processes that you use in microtechnology to nanotechnology. And that includes the use of photoresist. And so the idea was to place nanostructures inside of photoresist, use dielectrophoresis to align them across electrodes, and just continue then on with the processing that you would standardly do for microprocessing. In the end, burying the electrodes across the, burying the nanostructure in the electrodes, as shown here. This is a nanostructure, microelectrodes. There's a top and bottom contact to it. This was aligned during processing with photoresist mixed with dielectrophoresis. And we've done this for different types of systems: tin oxide, carbon nanotubes, and this was a different system that had to do with templating. And that templating was the idea that you coated in this case, a carbon nanotube with tin oxide and burned off the carbon nanotube. Some of the sensing properties of the, that is, ability to measure, say, methane at room temperature, seemed to be then passed on to tin oxide that does not typically have those sensing properties. And so, using this technique, one can also attempt to go to full wafer production, where one is able to, across a full wafer, do the photoresist processing combined with dielectrophoresis. And be able to then, and so this is again having to do with the templated approach, and the ability to measure things at room temperature that you could not standardly. Where I think things should go associated with nanotechnology might be summarized on this slide. We're used to effectively lock and key systems. The idea that you have a sensor that's a receptor, that is a lock, and the sensor, the species goes into that, is the key that goes into that lock. Well, there are a lot of keys that can go into the lock. And so the suggestion is, and to answer the question is, what is nano good for, potentially in the area of chemical sensors, is not necessarily small nanostructures for billions of molecules, but hopefully, as time goes on, nanostructures for the detection on the molecular level, to effectively range the sensor structure so that it fits the molecule in question and is in fact a well-designed lock to the individual keys that might go in. Tailor, effectively designed sensors for individual types of molecule selection. So in summary, and after multiple technical failures at this point, what I'd like to say is this. One of our mantras associated with this work is smart, small, and rugged. The idea that multi-use micro-nano sensor technology combined with intelligent hardware can enable smart sensor systems and drive the intelligence to the local level, whether it be a vehicle, whether it be an environment or an application. A future vision is designer diagnostics monitoring systems to optimize situational awareness, tailored to the individual application environment. Diagnostic systems, we can see, hear, smell, feel, process information, and communicate and self-reconfigure all in a miniaturized field applicable systems that can be on site, whether it be hot, whether it be cryogenic, whether it be ambient temperatures, being able to be where it needs to be in order to operate. One can imagine future combining this with a sample handling approach in order to, for example, potentially precondition the gas before it reaches the sensor. A Nano must be shown to have demonstrated advantages for a given application, and we talked about a template approach that is associated with being able to use other materials as templates for other high temperature materials, but we've also talked about microfabrication approach to mix microfabrication processing techniques with nanotechnology. In the end, one wants to do something with the data. If you can diagnose a situation, then one should be able to then take mitigation. The idea of the information is to be able to do something about it. And so that's the presentation. I think we're about on time.